For my 1631 final project, I added integral feedback to LQR to try and reduce the steady-state altitude error on a Parrot Minidrone. The drone is modeled as a 12-state system, so the model keeps track of x, y, z position, roll, pitch, yaw orientation, and their derivatives. The goal of this controller is to hover at a height of 1 meter. As we will see in the first clip, LQR on this 12-state system is not enough to hover at a constant height. Here's a graph of how high the quadcopter thought it was during that flight. The green is where it should be, and the yellow and orange are where it thinks it is. Even at the end, when it looked pretty stable, it was still over 40 centimeters higher than it was supposed to be. To try and improve this, I added a 13th state to the quadcopter model, which is the integral of the altitude. Using this new model, I regenerated the gain matrix using LQR. The reason integral feedback should help is because even if the quadcopter reaches a steady hovering height, if it isn't exactly at the height it should be, the integral of the error will keep growing and growing, which will force the motors to compensate for it. As you'll see in the second clip, the hovering height is way more constant. And it's even more clear on the altitude estimate graph. Near the end of the 20-second flight, the altitude error was less than 1 centimeter. So, adding integral feedback to LQR successfully decreased steady-state altitude error on the Parrot Minidrone.